Welcome. Hi, everybody. Glad you're here. We're going to come back to 6.4 in just a second, but for right now, 6.3, and I need to unfreeze that silly screen. Here we go. Ready, set, let's go. Okay. We're using properties, and so if you guys notice, a lot of this isn't going to be solving. It's more just knowing how to play with all the pieces, right? So number 2 was 2. That's ironic. That's A, though. B was 9. C was -2. D was 1. E was -6. F was 1. Is there more? Oh, no. One more time. Sorry, one more time. Number 2. A was 2. B was 9. C was -2. D was 1. E was, bless you, -6. F was 1. We got it? Okay. Moving on. Number 12 is -3/2. Oh, sorry, -3/2. No. -3/2 was the definite integral. And then you had to find the special C, which ended up being plus or minus √3. Just kidding. MBT says only the one inside, so only positive √3. Number 16 was a plug and chug. It was a plug and chug using the geometry. And so I think we had a rectangle minus a half circle. Does that sound about right? And that would have been the average value of F. Careful. That's not the average value. That's the definite integral part. The average value is 1 over b minus a. So we had that times 1/2, hence why the final answer is over 4. Or I guess you could have 1 minus pi over 4, but that's kind of awkward. Number 22 ends up being 1. Unit circle, did you know it? Trig, antiderivatives, do you know them? Number 26, using the properties, you end up with 32. If you use the properties, you could have also used an antiderivative. Or you could have done the area of a rectangle, height of 8 and a base of 4. Done. Any constant functions, just a rectangle. Number 36, the average value. We needed the definite integral, which was a simple secant antiderivative, but we also needed 1 over b minus a. Hence the final answer, 3 over pi. Number 48 is D as in delta, and 50 is C as in cataclysmic. You're welcome. I don't know, it's the first word that popped up in my head. Or like Calvin and Hobbes. I was thinking Calvin and Hobbes too. Cat. Sure. Isn't it Charlie? C is for Charlie, if you're actually doing that. N is in Nancy, M is in Mary, C is in Charlie. What's A?
Alpha.
Alpha? It is alpha?
Alpha.
Oh, alpha beta. Well, it's weird. There's like names for like half the letters, and then there's like Greek letters for the other half. But I guess they did Greek, and then they did names where Greek didn't work.
Epsilon is Foxtrot.
Oh, Foxtrot's not a name. Anyway, sorry. We're done, right? Okay, questions on 6.3. Questions on 6.3. Odds or evens? Going once. There you go. Number 7. Anything else? Going twice. Sold. Number 7. Catch me if you figure out that you have a quick question after number 7. Number 7's directions were just solve, I think. Find dy. No, I'm in 6.4. Yeah. Don't worry, AJ. I got it. I was in the wrong section. I got it. I need to go find him. Show that the value cannot possibly be 2. Whoa! It's like I'm supposed to know what this falls in between, even though I have absolutely no way of solving for the antiderivative. This sounds very AP concept-ish, right? Why did I choose this one? Because I liked it. And it made you ready. Are your notes open? We're going back there in half a second anyway. Remember how there were 2 new properties in section 6.3? One had to do with dominance. This is not that. What was the other one? Max and min. Max and min doesn't tell me how high it can go, how low it can go. And maybe this is outside the how high, how low. Does that make sense? Ooh. So, how high can this go? How low can this go? What do I need to think about for how high and how low an integral can go? Max and min values. Because aren't these, guys, this is the function. I'm trying to find the area underneath, right? So aren't these sine of x squared, aren't they my heights if I'm thinking about area, right? My f of values that drawing the rectangles up to, true? So I can find my max height and my min height On what interval? If I can find my max and my min, won't I know the highest this area can be, the biggest rectangle, the max in your property, or the lowest this area can be, the min rectangle? True? Now, think of sine of x squared. Do we really want to find the max and min using calculus and, like, I don't know, chain rules? Maybe. But can we think about whether we know if he's strictly increasing or decreasing on that interval? Because strictly increasing, wouldn't the lowest be here, the highest be here? Strictly decreasing, however it's decreasing, the highest and the lowest. Do we know that about sine of x squared? The maximum sine in general can get is 1. Is that accomplished on this interval? When does sine equal 1? What Lorenzo's thinking, and we can also think of it the other way, right? The max sine can get is 1, the min sine can get is negative 1. True? I'm asking when does sine hit 1, so we can think about whether or not it can be accomplished here, right? So when can sine equal 1 is at theta equals pi over 2. Pi over 2 is what kind of value? It's 3-ish over 2-ish, right? Which is 1 point something-ish. Okay, if I square any numbers between 0 and 1, including 0, including 1, will it get up to something over 1? Aren't any of the numbers in between 0 and 1 squared, aren't they smaller? Like 1/2 squared is 1/4, and then 3/4 squared is 9/16, and then, right? And then 1 squared is 1. Is it ever going to get up to this? No, which means, ooh, think about it, and wait a minute. Sine of theta, well, hold on. So sine of 1 is going up towards the max, but not getting there. And sine of 0, where's that at? 0. So in between 0 and 1, don't I know that it's kind of like headed up towards its max, but not quite there yet? Don't I know it's this kind of piece? Why am I doing this? If this was a multiple choice, I wouldn't want to be actually taking like a chain rule and trying to find my critical numbers and my types. Maybe it's faster for you. But for me, if I can figure out strictly increasing, what does that mean? Where's the max of sine of x squared? Well, it's going to be at 1. So the max is going to be sine of 1 because my function is strictly increasing. Where's the min going to be? Well, it's the lowest of that strictly increasing piece, which is going to be sine of 0, which is 0. But I don't know sine of 1. Okay, well, Lorenzo, now it's time for his trick. What do we know this is at least less than? It's bounded by something lower than 1, right? I don't know what it is, but something lower than 1. It's not a unit circle. Somewhere between pi over, what, pi over 3? No, it's a little bit over 1. Somewhere between pi over 4 and pi over 3. Somewhere in there. But it's something less than 1. Or I should say, somewhere between root 3 over 2 and 1. My bad. I'm saying the value is not the increase. But anyway, long story short, I know it's less than 1, so what does that mean? What's the biggest this rectangle can be? Isn't this a base of 1 and a height of 1? Because it's when sine gets to 1, then it keeps going, right? And this is somewhere smaller. And then this is, well, that's just 0. So question, where's 2 in all of this? Could this area possibly hit this area? No, there's no way. So one way of talking about it is you could say that, hey, the max of sine of x squared is sine of 1. So we could say that the integral from 0 to 1 of sine of x squared dx is somewhere between, we can put or equal to if we want, but we know the nature of sine is not going to equal those. That's going to definitely be an upper bound and a lower bound. It's going to be between sine of 0 times, that's the height, times the base is 1, and then sine of 1 times 1, because that's my max value, and that's my min value. I know this is less than 1. 1 times 1 is not getting anywhere close to 2. 2 is not included in that interval at all, so therefore, nope. Maximum inequality, it's impossible. It's not even close. It's going to be somewhere between 0, which is what this guy equals, and something less than 1. I can just put less than 1 for this quantity over here. But that was all the max min, that new inequality that we learned. All right, cool kids. With that, no more homework questions. Going once, twice, and solve. Okay, here we go. Section 6.4. Let's go play with FTC. Whoa! Why do I have so much space on this page? Let's see what else is coming. Make it big. Let's try to zoom in. FTC, fundamental theorem of calculus. Which is weird, because I think you were supposed to kind of do antiderivatives in the last section, but I don't think they actually named FTC at all in the actual content. If you guys looked at it, there's more of like a, hey, it works, I think, by mean value theorem, and so let's go for it. But FTC, this section starts off with the antiderivative part, which last year was FTC part 2. This year it's technically FTC part 1. What? Different books name it different ways. Some name it on which one came first. Some name it on like the actual order of importance. Some name it on, I don't know what they were feeling that day. I'm sure there was more logic to it than that. But long story short, guys, don't memorize who's who. Just memorize what it means. So if I have, what's the name of this type of function? We reviewed it just the other day. When I have an actual function in terms of x with a definite integral with an x bound. Accumulator, good. This is my accumulator function. Because this x, as it increases, accumulates more and more and more area, or as it decreases, accumulates less and less and less. I'm accumulating error. Has a derivative at every point x in a to b such that f prime, you guys know the AP, it's not going to say df dx, probably not. It's going to use f prime of x. It's going to name it like an f or a g or a whatever. The derivative is the derivative of the definite integral, which derivatives and integrals have this inverse relationship. Remember, it's not quite as nice and neat as ln of e or e to the ln or square root of squared. All of that can be messy sometimes. It's really nice when it's d dx from a to x. So nice, so easy. Basically, they undo each other, and I just have the integrand left as my function. The f prime is the integrand, or the little f of x. But what do I have down here, and why do I have space beneath it? What if the accumulator function is not from a to x, but a to u? According to FTC, the other part, can't I say this is equal to the antiderivative from a to u, right? And couldn't I actually, even if I don't know who the heck he is, couldn't I actually like start to plug in stuff in notation? And then couldn't I, if this is g of x, couldn't I talk about how to find g prime of x? What would g prime of x be, guys? Well, wouldn't it technically be, I mean, just go through the rules, right? But yeah, hold on. So it'd be capital F prime of u times u prime minus, well, capital F prime of a times a prime, but a is a constant, so what's that whole thing? Oh, the whole thing is a constant. Oh. Now, why did Lainey say a second ago, and I shushed her real quick, why did she say lowercase, and I was like, shh, not yet. The antiderivative's derivative is the original, right? So therefore I can say, oh, that's right, there was a variation on the FTC last year, that if I take the derivative of the accumulator function with an a to u, it's just f of u. And you, remember him? And that's just a reminder of why. Last year I showed you why. It might not have made any sense. This year maybe you're like, oh, hey, it actually makes sense. Maybe it made sense both years. If so, applause. So far, so good? Okay. I mean antiderivative part because, wait, did I name this one? What did I name the other one? Hold on, pause. Where's the other guy? In my head, I don't know why, but it's not making sense. Oh, evaluation. Okay, got it. Oh, Santa. There we go. do the antiderivative part and then the evaluation part. The antiderivative part, we're actually talking about, in a sense, the integral of the accumulator derived. So the derivative of the antiderivative is ultimately what's going on. So there's a deriving process. And then the evaluation part is actually how to solve for definite integrals. So, I don't think you guys necessarily need me to like pause all the class and have you try them. I'm going to give you 30 seconds to write down each one, and then we'll go straight to the answer. Sound good? There are directions for all of them. Solve. No. Find the derivative. Let's see if it gets hard or if it's just going to be basic. Okay. Bless you. Is it going to be that time of year again? I feel like it is. The sickness. The sickness is going to start to hit. Depends on the year what it actually is, right? For number 4, you guys got it already, right? What'd you get? So we have to take the derivative of this side and the derivative of that side, and this is FTC part, whatever you want to call it. So what'd you get? Square root of? You guys agree? It's a simple a to u. We don't care what the a was, we just care that, oh, and the u is x. So you want to think about it. Plug in the x, and then u prime, x prime is just 4. That's basic. How about number 16? I'm going to put a big old negative first. It's flipped, so to flip the bounds, right? We can flip our b to a by throwing in a negative. And my a is 25, to do it, it's just about the 25 in any way, shape, or form. No, because his derivative when plugged into the antiderivative is 0. It doesn't matter. What does matter is, if we were being super safe of a long answer, we'd be doing this, right? But am I done? What do I need? Right? Take your entire integram, plug in the entire u, the upper bound. And then u prime. Yeah, I'm okay sticking it to the man if you guys are. We all good? Now wait, what if I didn't put parentheses? What would have gotten us? The negative, right? That needs to distribute. Or you could have put the negative with the 10. Just think about multiple choice answers. You could have put the negative with the 10 and then it might have been okay. Just make sure it's not minus 10x. It's times 10. You could, as long as you make sure the parentheses. The same problem is we need to make sure that this either distributes to everyone or shows mathematically that it is distributed. Be careful. Number 20. Ooh, this is exciting. Now some of you are like, I would just anti-derive and plug in, and take the derivative. Okay, you could, but come on, there's another way. Remember the AP doesn't always give you somebody who can actually anti-derive. I hear you. You're thinking. What do you want to do? Do you want to just keep it general or do you want to make it now? General? Okay. So what if we do, you said C, Lorenzo? Are we allowed to do that? Where are we splitting it up? I don't know. 0, pi over 2, pi over 4, a million, negative 17. My high school basketball number of 42. I don't care. Whatever you want. I'm just keeping it a general constant because the point is it doesn't matter, right? Now, what does matter? What am I going to do right here? Yeah, I need to go from A to U. That does matter. The direction that we're going when we're accumulating. I don't like using that word when we're finding the area. But remember, guys, we're finding the derivative, which means we're deriving this guy, which means we're deriving this guy, which means we're deriving this guy, which is why we're using FTC. We're taking derivatives of integrals, yeah? So negative, what's the first piece going to be? Sine square root of x. Let's use the proper notation. But what else? Nope. Times cosine. Got your u prime, right? That's of u times u prime. Now plus. U prime. Remember, only he had the negative originally because of the switching of the bounds. He was totally fine. Then we're just doing that notation where if we plug in a cosine is squared, it's not cosine of x squared, it's cosine squared of x. I mean, you could pull out a sine and a cosine if you really wanted to. You could pull out a negative sine and a cosine. I know, I'm making it match now. I know. But still, we have to make at least one of them match. What's left inside? Yeah. You guys know these will probably be multiple choice anyway, right? Okay. Your turn. Have fun with number 25. We played a little bit. Now it's your turn. Ready, set? I'll give you a couple minutes. Ooh, we get to construct a function. That's fun. There. You are making your very own accumulator function. Those are probably the only pieces you're solving. You might need to throw in a bound too. A and F of T and C. What did you guys put as the integrand? I think that was the easiest part. I might be wrong. I don't mean that any of it's easy. It's an interesting question. It's uniquely put, right? But what did you put inside your integral?
So like a constant and then 5x.
Well, it needs to be in terms of t. Kevin, what was yours again?
So mine was like the integrand and like a constant of 5x, and then the function was 1/5.
Oh, I meant the integrand. Sorry, these are the limits.
Oh, my bad.
So what's the equation?
1/5 cosine squared t.
Oh, we did it that way. What if you left this as an x? That's what I was assuming. I was assuming we would leave that as an x. Yeah, cosine squared 5t. It's that easy. right? Now, I do need a constant in the bottom, I get that, but hold on, the derivative of that, any constant to x, wouldn't that just be cosine squared of 5x, right? Now, here's where it gets interesting. Did you figure out how to do this such that that was negative 2? If it's 7 to 7, wouldn't that just be 0, so it doesn't even matter, so the negative 2 is my constant? No, it's good. Now, this didn't tell me the 7 had to be that. But do you know how to anti-derive cosine squared of 5t? I don't. I'm not going to go actually anti-deriving. I'm just going to say whatever. If I can make this whatever I want it to be, sure. Let's do 7, so that way 7 to 7 is 0, and I can make that my initial condition. The bottom limit was an unknown, so I was able to make it whatever I wanted. So 7 to 7, sweet. I'm done. But Kevin, yours with the 1/5 would have been fine. He put a 5x up here that way when you... Now, your bound would have had to be different. Your bound would have had to have been 35 if you did 5x. So that way when you plugged in 7, 35 to 35 would get you the negative 2. But the 5x, the 1/5 would have been fine because then you would have gone ahead and done 1/5 cosine squared of 5 of just x, right? Of 5x times 0.5 and 1/5. Yeah, you would just need your bottom bound to be 35. Whew, that was an interesting question. I like that one. Very uniquely put. Let me make this red real fast because we do that whenever we answer questions. I just made it black for whatever reason. Okay. This, I don't know. You guys see accumulator functions a lot on the AP. Not so much, I don't know, not so much throughout all of the multiple choice and all of the long answers, but every year there are accumulator functions. You might be like, what? Are they just trying to like screw with us? Or are they just trying to confuse us with variables and the bounds? So I liked how our book, because our book just has some really interesting concepts or conceptual treatments of the material, trying to give you like a bigger picture of what's going on. So I liked when our book said it's difficult to overestimate the power of the equation, which is what we've been working with. The accumulator function and a derivative of the accumulator function. Because this statement says, or the two statements above say that every continuous function f is the derivative of some other function, the accumulator. It says that every continuous function has an antiderivative. And it says that the processes of integration and differentiation are inverses of each other. If any equation deserves to be called a fundamental theorem of calculus, this one is truly the one. Because it has this relationship of derivatives, antiderivatives, the inverse between them, and you guys know that Calc 1, derivatives whole first semester, antiderivatives in some sense, whole second semester, and then this one ties them all together in one derivative. So, anyway, that's, I think, why our book chooses to make this part 1, because this is the whole foundation to this relationship between derivatives and antiderivatives that it finds so important. But, is that all there is to FTC? No. Part 2. Application. Which last year we learned this one first, and then we saw it being applied to that whole inverse relationship. This year it's a little bit backwards. And I showed you how the ATU thing worked by finding an antiderivative, so I kind of cheated. I went to the second part and used it in order to show you why it works. Maybe that's a little bit rough. Another reason why last year's book called this part 1, because then you can build on it to show why part 2 is true, especially from ADU. But anyway, you can dig a little deeper as to whether or which part should truly be part 1 and part 2. It doesn't really matter once again. You know that all of it's true and you're able to use it. I underline 2 things. F has to be continuous, and capital F is just denoting the antiderivative. But you guys know that AP can make the antiderivative G or H or whatever they want to call it. Like with inverses. They say like G is the inverse. They don't really show you the F -1 notation. So just be ready. But, really quickly, FT FTC deals with continuous functions. However, do you remember from an earlier section that we talked about how continuous functions aren't the only integrable functions? Remember? We could have that, what was it? Was it the absolute value of x over x? You don't have to write this down. But remember how that was that whole -1 and then 1? Couldn't we still find area under this curve if we wanted to, right? That one hole, that one discontinuity doesn't make it so that we can't anti-derive. It doesn't, well, I should say, doesn't mean that we can't have a definite integral and it doesn't exist. The definite integral would exist for something that's not continuous, but FTC specifically, this whole idea of antiderivative of b minus antiderivative of a to solve for it only works with continuous functions. Does the distinction make sense? Discontinuous functions can have area under, can have integral answers, but just FTC couldn't solve for it, or shouldn't be used to solve for it. Okay, so what do we have, guys? This is basic stuff that, to be honest, I think you've kind of been using for a few sections now, which is really weird. Another reason why I have this book being BC, because to be honest, I'm not exactly sure how I would totally teach. If you guys notice, like you're supposed to all of a sudden know antiderivative rules, and we haven't really talked about them. It's kind of awkward, but that's okay. You know antiderivative rules. Number 30, how do we antiderive? Power rule, which means this came down 1 from add 1, right? What's 3/2 plus 2 over 2? And we have to offset by the constant when it comes down, right? So I have x to the n plus 1 all over n plus 1, or the reciprocal of the new power, times the old power plus 1. Wait a minute, plus c. No, because what kind of integral is this? Definite. So we have our 0, we have our 5. Do we remember exponent rules and how to actually solve if we had to make it match? Some of you just got stuck. The nice thing is, plugging in 0 is just 0. So I can forget that part, right? But I can't forget this part. So what do I do when I have 5 to the 5 halves? Am I a little scared some of you couldn't do this? Wow. Go team. Okay, if I go to square root, I do this, and I do this, and I do this. And we figure it out? Ugh, that's gross. Why? Why can't we just make this 5 to the 2 1/2? Right? 2 1/2. The half one is the guy that's under the root, the 2 is the 25, and then that's going to be 10 root 5. Anyway, do you guys see why I'm still having homework to do tomorrow? Because what's the end? Antiderivative. Sorry, FTC. Solve with FTC, antiderivatives, plugging in the bounds. Good job, guys.